Hello, my name is Chris Merchant. I'm at the University of Reading in the UK, and the topic in this poster is restoring sea surface temperature gradients in level 4 GHRSST products. A level 4 GHRSST product is one that's been gap filled. Most of our observations are made from infrared sensors, and those are only available to give us sea surface temperature under clear sky conditions. And so many of the input products to a gap-filled analysis for the whole global ocean include gaps where there are clouds. Now, gap filling across those cloudy areas, of course, is hugely beneficial to users. It simplifies the use of our sea surface temperature products, which is why it's done. But it has a knock-on effect on areas that we did actually observe. And this is shown in the figures at the top here. On the left, there is a level 4 gap-filled product from the ESA Climate Change Initiative. It's for an area of the Gulf Stream in the North Atlantic on a particular day. And you can see that it includes some nice features. We have some strong gradients and a lot of spatial variability of temperature. It so happens that this area was observed under clear sky conditions on this particular day by two AVHRRs on the METOP platforms. And I've combined those two platforms into a level 3 gridded product on the right. You can see there's a lot of compatibility with the level 4 analysis, of course, because those observations were some of the observations that went into that level 4 analysis. But there's also a lot of difference in the feature fidelity. The gradients that we actually observed in the level 3 product are sharper than the gradients in the level 4 product, and we can see some features in the level 3 that are completely smoothed over in the level 4 analysis. And that seems a shame. After all, we did observe these features. It's a pity not to have them present in the level 4 analysis, given that we did have clear sky observations of that area on this particular day. But we don't want to throw away some of the benefits of the level 4 analysis. It's not just about gap filling. The level 4 analysis also blends the data from many different missions, and that gives us an element of bias correction that we want to preserve. So it's not just a case of dropping the level 3 in to the areas where we have observations instead of the level 4. We've got to do something a little bit smarter. And this is one solution to that problem. Essentially, if we call the level 4 analysis, this field, this two-dimensional field, a matrix Z, and we've got observations that we're going to refer to as a matrix Y, what we want to do is adjust this matrix Z to look a bit more like the matrix Y in terms of the features that are present. And restoring the features essentially means restoring the gradients that are present in the level 3 product. But we want to do this in such a way that we preserve the overall absolute SST level in the level 4 because of these benefits of blending multiple sensors that I mentioned. So it's a trade-off, and we can formulate any trade-off in general as some sort of cost function, and that's what I've done here. The adjustment delta Z is represented in the first term, and we want to find the smallest adjustments that we can that fit with restoring the features. The gradients in the east-west direction are represented by the second term. You can see that we're comparing the gradient of the restored level 4 analysis plus adjustment to the gradients in the observations from the AVHRRs. And the cost function has a term representing the difference between that restored level 4 gradient and the observed gradient. The gradient operators are given by these differentials. And there's a similar term for the north-south gradients. So this is the north-south gradient difference between the restored solution and the original observations. We find that restored solution delta Z by minimizing this cost function with respect to delta Z. That's found by finding the derivative of the cost function with respect to delta Z and setting that equal to 0. So there's a bit of mathematics involved in finding the actual solution, but it turns out to be a relatively tractable linear equation which gives us an estimate for a correction, delta Z. And that can be added to the level 4 analysis, giving us a sharpened result. So this is shown for this particular case in the figure bottom left. We see that the overall SST levels are very well matched to the level 4 analysis that we looked at before, but also the features that are present in the original level 3 product are very well preserved in this compromise as well. And so it's a sharpened solution for the level 4 in the area of clear skies. And it preserves the desirable properties of the level 4 analysis otherwise. So this is achieving something quite similar in one sense to the sorts of multi-scale analyses that have also been tried in the GRIS community very successfully as a way of preserving full feature resolution when we have clear skies, but still achieving gap filling where these are not available. It does, of course, beg the question of what to do about the areas that are gap filled. Is there anything that can be done to address the feature resolution in those areas? Basically, we can either say, no, they're not observed, and only restore the gradients where we have clear skies. That keeps us close to what's actually observed as best as we can, but of course it does mean that we're left with a product that would have a variable feature resolution, with the gradients only restored to full value in the areas that had good clear sky observations. Alternatively, we could use results like this in the places that we have clear observations to learn how to sharpen up the level 4 analysis. That could be a machine learning example, and there have been a number of attempts at this sort of super resolution approach already, which have looked very promising. Of course, that would then give us a more uniform feature resolution across the whole world, across the whole analysis, at the expense that those features are to some degree invented by the machine learning process. They might reflect the sorts of statistics that can happen for the SST distribution in the ocean, but they're not actually based on observations. And which is the best solution? Well, it probably depends on the user application. So I'm very keen, if anyone has opinions about which sort of solution they would find most relevant for their application, to hear from you. And my email address is on the PDF version of this poster. So in summary, it is possible in a relatively simple way to reintroduce the full feature fidelity into a level 4 product where we have clear sky observations using this sort of cost function analysis. Should we do that and end up with a variable feature resolution product? Or should we try to go down the super resolution route and learn how to do this across the world without necessarily having observed all those areas in reality? That's an interesting question, and I'm very interested to hear anyone's views on it. And thank you for your attention to this poster.